just another day.
Oh, I found it. I found it.
What is it, Vic?
It is 320.
What did you find?
320.
320 what?
For B.
Oh, whatever. Okay. This is the last of the terms that I started out in the last period showing you. But this one's going to take a little bit more explanation than the other ones did, I think. Enthalpy.
That's true.
Now, if you look at the symbol for enthalpy, it's delta H, which kind of gives us a clue as to what it really means. Delta usually means what? Change, and H stands kind of for heat. So it's the heat change. If I carry out a reaction, whether it's physical or chemical change, I want to calculate how much heat change there was. That's basically what I'm trying to do, find out the difference between before and after. Okay? The heat gained or lost by a system. Now, it is a function of three things. See if you can tell me what they are. This is funny. I do this I'm going to spend a little bit of time on this. Like I said, I wanted to spend some time on this one. The actual amount of notes you're going to end up taking here is going to be one board. Okay, it's not like we're going to have a whole lot of notes. I said that. However, I want to spend some time seeing if you can give me the equation for delta H. So a lot of times you guys just memorize things. You have no idea where it came from. For example, D equals M over V. You know that's the equation for what? Density, you know? And you kind of just memorized it, and that's your equation. The one I just did for Celsius, okay? And they don't really make sense to you, but they should. And this is one that does make complete sense. I want you to think of the three things. There are three factors. Write these down. Write this down. You tell me what the three factors are that would determine how easy or hard it is to heat up something or to cool something down, either way you want to look at it. What's one factor? Give me one factor. Read.
Volume.
Well, not necessarily volume, but another measurement that would be something like volume for the amount. Mass. Mass is we're definitely going to use mass. Absolutely. The amount that's there, the mass of it, is going to be one. No, don't write it down. Okay, that's a good one. All right. What else? No. But all three of those you're talking about have to do with the second one. I can't remember what I put as the first one, but the first one, if I have a picture here to help you out, this one, there's more of it, right? So that's the mass one, right? You don't have to write this down, okay? You're only going to, like I said, you're going to think about a couple more lines of notes is all. This guy's bigger. It would obviously take longer to heat this guy up. That illustrates one of the factors. If you can't get the next one, let's see if another picture here might help you. Okay, think. So mass is the first one.
Temperature.
Exactly. If I have the same amount, assume I have the same amount, right? If I want to heat one to 60 degrees and I want to heat the other one over to 20 degrees, won't it take more energy to heat this guy up? Even though there's the same amount of it there. You see? So mass is one thing, temperature is another. But there's a third one. And that third one was the one you guys were all hinting at, saying stuff like density, surface area, stuff, what it is you're heating. Exactly. This guy, if he's made of something different, is going to, I have just different colors here. The specific heat tells us that. Those are your three factors. Absolutely. All right. Now, here that's nice. You can write all those down. Now, here's my challenge to you. Can you put those three things into an equation that makes sense? It has to make sense. Look here, guys. We're going to use for mass, I want you to use M. And for specific heat or temperature, you just use T. And for specific heat, C. So those are your three variables. And, of course, delta H equals is what you're going to start out with. So everybody think about that. Delta H equals. Write that down underneath this. What do you think delta H equals? How will I arrange M, C, and T together? How will they have to be arranged in order to get the correct answer? Look at the units. That's always a clue. Look at the units. What do you think my units of heat have to be in? Calories or joules, right? Joules or calories. Okay, so we'll say, we know he has to be in joules or calories. What does mass have to be in? Grams, right? What does temperature have to be in? Celsius, degrees Celsius. And what is specific heat? What are the units for specific heat? Look at Appendix E. Now put all that together and figure out what the equation has to look like. What does the equation have to look like? Appendix E should have at the top what the units are. So what do I have to do with those variables? What is the equation going to look like? Who wants to give it to me?
Joules per gram Celsius.
That's not an equation. It's not an equation. I want an equation. D equals M over V is an equation. Delta H equals what in terms of M, C, and delta and T?
Multiply all those.
Okay, tell me what to write. Then delta H equals
Delta H equals
M
times T
times the absolute temperature.
times.
What are we trying to figure out? The energy lost or gained by the system. The actual number, the actual temperature I'm going to multiply by.
Temperature change.
The temperature change. Okay, so M, delta T, and one other thing. Well, no, what's the specific I told you to use for specific? C. That's the equation. That's the equation. The equation for this guy is delta H. Spread them out so I will put underneath what each of them M, C, delta T. The mass times the specific heat times the temperature change. You see, equations make sense. Density equals mass over volume because mass divided by volume tells me how dense something is, how much it weighs, how much its mass is, versus how large it is. A pound of feathers and a pound of lead, right? Which one's going to take up more space? Obviously, the pound of feathers takes up more space, right? So the density is not the same, even though the amount of them may be. Well, here, enthalpy, heat change, has to make sense. Because if you think about it, your mass is in grams. Your specific heat, as you looked up in Appendix E, is in joules per gram degrees Celsius. And your temperature change, after you subtract them, it's going to be how high you're heating it, will be in Celsius. So what happens? Celsius cancels, grams cancel, and what does it leave you with? Which is exactly what you want your energy to be in. If you had those arranged any other way, you would not get the correct units. It wouldn't make sense, is what I'm saying. If you had mass divided by C, or C divided by M, it wouldn't make sense. The reason equations look the way they do is that they have to work out. They have to make sense. All right, they actually mean something. And by the way, let's go back to, that's as far as the units go. Now let's go back to the reality of it. How much of it matters? It will be, the more mass I have, the more energy it's going to take to change its temperature. Specific heat's going to matter. If I'm heating up water, water we saw was really high, 4 point something. Same amount of water, same amount of iron, not going to take as much energy for the iron. And finally, how high I heat it will make the amount of energy higher, what temperature I heat it up to. All three of those factored together give me the delta H, or the heat change in this equation. Now, let's just do one quick example, and then you go back to doing your problems. I have a few other examples, a few other homework problems to do. Oh, by the way, one other thing I should mention, I always glad I added this because I always forget to say this at this time. You guys should know this. We talked about endo and exothermic back in the day, back in Chem 1, but I did not do this equation back then. So, you didn't know what positive or negative delta H would be. I kind of just had you, at one point, we kind of just memorized it, which was probably stupid. If I had time, I should have done it back in Chem 1. But you remember when we did heats of solution were positive or negative? We did talk about that. The reason makes complete sense. Think about it. The mass and the specific heat are always positive values. So the only thing that could be negative or positive. Is delta T. And notice how I have delta T written, TF minus TI. The final minus the initial. So I want you to think about this. If my final temperature is 100 degrees and I started at 10, so I started at 10 and I added energy to him to get him up to 100, right? I heated him up. He was absorbing energy. I'm going to get a positive value, right? And that's going to be, and if I'm adding energy to it, if it's absorbing energy, it's going to be endothermic. If energy is being released, it's cooling down. Okay, say it starts at 10 or 100 degrees and it ends at 10. It's going to be backwards. 10 minus 100 will give me a negative value, and therefore he's giving off that much energy. It's going to be giving that much energy off. Okay, so that's why delta H being negative is always going to be exothermic. Delta H being positive, energy is released. And by the way, that's going to favor spontaneity. You know why it favors spontaneity? What do I mean by spontaneous? Happens by itself, right? What does everything seek? Remember, in Chem 1, the first day of notes, I use this as my first demonstration, I believe. What's going to happen when I drop this pen? It's going to go to the ceiling, or is it going to go to the floor? Ceiling. It's going to go down. It's going to go down because there are two driving forces in nature. Everything seeks its lowest energy state. And what's the other driving force? Do you remember that one from Chem 1? It was a long time ago. Entropy. Everything seeks its highest entropy state. We're going to talk about that again in this chapter. So it should not surprise us that if delta H is negative and things are seeking a lower energy state, that's natural, that's spontaneous. That's what's going to favor spontaneous reactions, energy being released. If I have to add energy to it, remember another way we looked at it was this way. Remember this equation like this versus this equation like that? The endo and exothermic, we did them that way. The hill. Things naturally go downhill, things don't naturally go uphill. This one was endo. This one was exo. Now remember talking about spontaneity in that? Remember that? Okay, we did do it in Chem 1 as well. But I always forget to mention here, I'm glad I added this to my notes last time. All right, so again, of course the opposite is true. If delta H is positive, it's endothermic, and therefore energy is absorbed. A lot of the stuff that I'm saying here, you've heard me say before. We're just going to do in more detail now that we're in Chem 2. As a matter of fact, I don't think, with the exception of specific heat, the actual calculation for specific heat and the actual calculation for Fahrenheit and Celsius, there's nothing so far that we didn't talk about before. I mean, yes, I'm putting all this together into a new equation, but all of these things we kind of talked about before. Endo versus exothermic reactions, spontaneous, not spontaneous. Heat versus temperature. All of that stuff was stuff we talked about before. We're just doing a little bit further each time. Okay, let's do our only example. That's all the notes we have. Our only example will be this one. Calculate that. Write that down and we'll do this calculation. It's a very simple problem. And by the way, the amount I'm going to add on to your homework here is not going to add a whole lot to your homework. What time is it over? 19? Okay, well, you'll have to finish this for homework, but there aren't very many. And you can go back to it in a minute. The other class will have a double tomorrow. They won't have any time to work on it today, but they'll have time tomorrow. And remember, I don't check the homework the very next day. If I haven't had a whole lot of homework this year, maybe you haven't had me for a couple of years, you may not remember that. It's not like, oh, I got to struggle. I'm not going to check the homework the very next day. All right, now, what would I want for work on this problem? Same as I would always like. I want the formula, the numbers plugged in, and then the answer. Now, with an equation like this, what's the formula? Delta H equals MC delta T, correct? All right. Where delta T is TF minus TI. I mean, you can write TF minus TI so you don't accidentally do them backwards. That's fine. All right. Delta H, therefore, equals the mass. What's my mass in this problem? 10.0 grams. Hey, guess what else we're going to have to keep in track of? Significant figures. Yes. You missed them, didn't you? 10.0 grams times the specific heat of water. Now, I purposely made it water, and the easier number to use for water, I can use either one of two numbers. What two numbers can I use for water? 1 calorie per gram degree Celsius, or 4.184. I'll use 1. It's easy. 1 point. And I don't even have to put 1 point. Since he's our standard, he's an exact number. There's no 1.00 infinite number of zeros. He's our standard. Calorie per gram degree Celsius. Times TF minus TI. What's my final temperature? 40.